Good afternoon, Chair. Good afternoon, everyone. My lecture's topic is in-Situ measurement method for thermal-induced package stress in distributed MEMS phase shifter. I'm sorry. This is it's initial idea. Some preliminary work. I tried to explain it as detailed as possible. In our previous research work, the relationship between the thermally induced package trace and the performance of distributed MEMS phase shifter was studied. The results showed the thermal trace induced from a die touch process has considerable influence on the phase shift characteristic of the devices. These are the phase shift characteristic before the packaging process. These are the phase shift character after the packaging process. And the deviation of the phase shifter is apparently related to the location of the devices on the chip. These are three devices corresponding to the deviation of the phase shift, which correspond to the distributed feature of the thermal packaging stress in the chip. So we think the measurement process of the phase shift of distributed MEMS phase shifter could be synchronously and conveniently used for evaluating the thermal stress induced from a packaging process. First, the principle. Here is a distributed MEMS phase shifter, a high impedance CW transmission line, period loaded with a certain number of MEMS switches. In a lumped elements model, the phase shift per unit length can be expressed as this. The CBU and the CBD are the switch capacitance in upstate and downstate positions, which can be expressed as this. The G is the gap height of the beam. For MEMS switches, its mechanical behavior of the beam generally can be modeled using a linear stiffness coefficient. The stiffness coefficient of double-anchored beam generally includes two parts. One is due to the material characteristics such as Young modulus, the moment of inertia. The other is due to the residual stress induced from the fabrication process, including the packaging steps. The latter generally expressed as this. So for packaging distributed IF MEMS phase shifter, the residual stress increase the stiffness of the beam. So under the same voltage, actuated voltage, the diffraction of the beam will decrease. That is, the gap height of the beam will remain larger. So the switch capacitance will decrease. Finally, the deviation of the phase shift will produce. So as indicated as above, the measurement of the thermal stress can be synchronously conducted with the measurement of phase shift of the devices. Based on the principle described above, a suggested measurement process is first measure the phase shift characteristic of devices before the packaging process and certain actuation voltage. Then measure the phase shift characteristic of the devices after the packaging process under the same actuation voltage. Adjusted the voltage to return the phase shift of the packaging devices to its initial value in the unpackaged state at some certain frequencies. Then finally calculating the thermal stress induced from the packaging process according to the variation of the actuation voltage based on the analytic model described above. Then case study for demonstrating of this method. We have not designed or fabricated a specialized sample for the measurement. Some ready-made chips are used. Here are some primary parameters of the devices. Here is the fabrication process, including the packaging steps. Here is a measurement process. Two devices number 1 and number 2 are selected for measurement. An Angeline vector network analyzer used for measuring the phase shift characteristic of the devices. DC supply set used for providing a tunable actuating voltage. Here are some measured results. The phase shift of the devices of number 1 and number 2 has obviously varied after the diode attaching process. This is the phase shift characteristic before the die attaching process. These are the These are the ones after the die attaching process. And the deviation of the phase shifts are different due to the location of the devices on the chip. For the device 1 and the device 2, respectively. These are the required increment of the actuation voltage and calculated thermal stress for devices number 1 and number 2. These are the thermal stress and the deviation of the phase shift of the devices for devices number 1 and number 2. From the figure, we can see the required incremental actuation voltage and calculated thermal stress are also varied with the location of the devices on the chip. Finally, the conclusion. There is the dependency among the deviation of the phase shift of the devices before and after a die attaching process. The incremental value of the actuation voltage to return the phase shift of the packaged devices to its initial value in the unpackaged state, and the thermally packaging stress induced in the chip from the process. So by measuring the incremental value of the actuation voltage for offsetting the deviation of the phase shift of the devices after the packaging process, the residual stress induced in the chip from the die attaching process can be figured out. Moreover, the obtained incremental value of the actuation voltage can be used as a bias voltage to offset the deviation of the phase shift of the devices due to the thermal stress during the measurement process of the phase shift characteristic of the devices. Some further work will be done to improve the measurement, such as model optimization, method optimization, especially design the sample fabrication and verification method. There are many methods for verification, but the convenient one is resonant frequency measurement process for the residual stress, shown as this. Thank you for your attention.